In the last slide deck, we constructed the derivative to represent quantitatively the idea of a local slope. The purpose of this slide deck is to develop an intuition that higher-order derivatives describe geometric properties of the plot of a function. We also want to develop an understanding of how the values of first, second, and higher-order derivatives can be combined to provide so-called power series expansions, which are useful for representing functions. This is analogous in sentiment to using decimal representation to provide a concrete description of a number. When we use decimal representation, we often truncate the number of places we use to write down a value. Moving to the right of the decimal point, each succeeding place becomes a smaller and smaller refinement, and at some point, the accuracy afforded by recording additional places might be unnecessary for a specific calculation. When shopping for groceries, prices are currently rounded to the nearest cent. Owing to the cost of manufacturing pennies and nickels, some people advocate the elimination of both of these coins, which means that prices would be rounded to the nearest dime. Following the same lines of sentiment, the successive terms in a judiciously constructed power series expansion can be regarded as increasingly fine corrections to the description of a function. Depending on the application, it might be necessary to retain only a handful of terms. The strategy of replacing a function with a truncated approximation is often used to simplify the equations that describe the time evolution of dynamical systems, including gene regulation networks and populations of interacting organisms. We divide this slide deck into 4 videos. The first 2 videos are conceptual. In this first video, we explain that a second-order derivative describes curvature. In the second video, we figure out how to construct a power series representation of a function from knowledge of its various derivatives. The third and fourth videos are worked examples. In the third video, we construct a power series representation for the sine function. Using an approximation to this series in the fourth video allows us to quickly obtain a decimal approximation for pi. We begin by showing that the second derivative can be regarded as the so-called curvature of a plot of a function. To present this idea graphically, we plot an example of a quadratic function. We decorate this plot with right triangles in order to measure rises and runs starting at a variety of locations. When calculating derivatives, we consider an unending succession of smaller and smaller triangles. However, the triangles illustrated here are already so small that it is difficult to see the separation between their hypotenuses and the plot of the function. They overlap. For the purposes of this sketch, we can accept the rise over runs of these triangles as local measurements of the slope of the quadratic function. We plot the instantaneous slope or so-called first derivative df dx against all the locations x0 that can serve as the anchors for the left-hand corners of the triangles. Whereas in the previous slide deck we would use the label x0, here we will adopt the common practice of replacing x0, the position at which the derivative df dx is evaluated, with instead simply x. We can evaluate the rise over run for the plot of df dx versus x to obtain its slope, and this is called the second derivative. For a quadratic function, the viewer can confirm that the derivative of the derivative is a constant. The notation d squared f dx squared is shorthand for d dx applied to df dx. In this example, the plot of f on x versus x descends from the left, passes through a nadir, and then ascends toward the right. The plot appears to be cupped or curved upward. When it descends, its slope is negative. When it bottoms out through the nadir, its slope momentarily passes through 0, and when it ascends toward the right, its slope is positive. These different values of slope are reflected in the plot of the first derivative. The plot of df dx versus x is ever increasing as it passes through negative values, through 0, and then through positive values, so df dx versus x has everywhere positive slope. The plot of the second derivative quantifies the slope of the plot of the first derivative. Thus, the plot of d squared f dx squared has everywhere positive value. It is important to observe that the value of the plot of d squared f dx squared evaluated at x equals 0 in this example is positive, indicating upward curvature of the plot of f on x versus x about that point. While d squared f dx squared is likewise positive everywhere else, it is important to pay particular attention to this position, x equals 0, to observe that a second derivative can be positive even when the first derivative and the underlying function are both 0. If the value of the plot of a function is changing, its first derivative will be non-zero. If the plot of a function has changing slope, meaning curvature, then the value of the first derivative will be changing, which means that the second derivative will be non-zero. The value of the second derivative of a function evaluated at a point x describes the local curvature of the plot of the function. In the slide deck on algebra, we understood how the value of a function evaluated at a point corresponded to the height of a plotted curve. In the previous slide deck on differentiation, we understood how the first derivative quantified the slope of the plotted curve. And in this video, we have just seen how the second derivative describes curvature. In this way, we are developing an intuition that higher-order derivatives are also associated with geometric interpretations. In this video, we started out with a known function and determined the plots of its derivative and second derivative. We looked at a plot of a function to identify its geometric features. In the next video, we will show how we can perform essentially the reverse procedure. We will show how a function can be reconstructed by piecing together descriptions of its geometric features embodied in its derivatives.